Welcome to the introductory video on projectile motion, which is Unit 6. In this video, we're going to cover the introduction to projectile motion and some basic ideas, and then in the following videos, we're going to do some math problems. In this unit as a whole, we have four objectives. Number one, we're going to understand, first of all, what a projectile is, since the unit's called projectile motion. Number two, we're going to draw motion diagrams for projectiles. Number three, we're going to analyze two-dimensional motion in X and Y components. And then finally, number four, we're going to use those components to solve for various problems using our kinematic equations that we learned back in Unit 3. Before we get started, let's go ahead and accomplish Objective 1, which is what is a projectile? A projectile is defined as an object that moves through the air. The only force acting on the object is the force of gravity. Now, theoretically speaking, or ideally speaking, there is no such thing as a projectile on Earth. And the reason for that is because in addition to force gravity, anything that's maybe traveling through the air has some sort of air resistance or drag or lift that's acting on it. So technically speaking, there is no projectile on Earth. However, in this physics course and most of your physics courses, they neglect air resistance, drag, and lift. So any sort of force that might alter the projectile as it moves through the air other than gravity is going to be ignored. Okay, so a projectile is defined as an object that only has the force of gravity acting on it. Now, in this unit, we're going to cover three basic types of projectile paths. In the first path, on the top left, you'll see a cannon that's firing a cannonball horizontally off of a cliff. You can see in that picture that the pathway that the projectile takes almost looks like a half parabola. In the second projectile path, which you see in the top right, that's going to be what we call a perfect parabola. And the reason we call it a perfect parabola is because it creates a perfect parabolic motion. Notice that the ball launches and lands from the same height. Finally, a projectile path number 3 is the one in the bottom middle, in which case the projectile is traveling in a full parabola, but it's not a perfect parabola. And that's because the launch height and the landing height are different. Each of these pathways are going to have their own videos that go with them in subsequent videos for this unit. This unit will just cover the introduction. Let's talk about the first path from a conceptual point of view. On the screen, you'll see a simulation. An airplane is flying, and at some point or time t, the airplane drops an object. Now, there's a couple things that I want you to notice as this simulation keeps playing over and over again. First of all, let's notice the plane. What do we know about the plane's motion? Well, you'll notice that it's creating a dot for every time interval. And notice that the dots for the plane, which are in blue, have the same distance in between them. So we can conclude that the plane is traveling at a constant velocity. And since the plane is only moving horizontally, we could say it's also a constant x velocity. Now, the object that was in the plane is also traveling at a constant velocity. Let's take, for example, I'm going to make some numbers up here. Let's say the plane was moving at 150 miles per hour. When the object was attached to the plane, or inside the plane, the object was also moving at 150 miles per hour. And both, like I said, since they're not rising or lowering, both were in the x direction. Now, at some point t, the object is dropped. Now, when the object is dropping, notice what's happening. First of all, let's notice what's happening in the x direction. In the x direction, or the horizontal, you'll notice that the arrow, which corresponds to the velocity of the ball, does not increase. Watch the horizontal arrow that's attached to the ball in this next video. Notice it does not get any longer. The x velocity remains constant. And if we look at the dots that the ball makes relative to the plane, you'll notice that the object dot lines perfectly below every blue dot that's for the plane. Now, why is that? Remember, a projectile is defined as an object whose only force acting on it is the force of gravity. And force of gravity always faces down towards the Earth. So that's the force diagram drawn to the right of the object as it moves through the air. There's a few things I'd like you to notice. First of all, what are the x forces that are acting on the object? And the answer is there are no x forces. If you analyze the force diagram in the horizontal direction, there are no x forces, because remember, we neglect air resistance, drag, or lift. So there's nothing acting on the object in the x direction, which means in a sense, it's an equilibrium. Remember from Unit 5 that it takes an unbalanced net force, or just a net force period, an unbalance of forces to make an object actually accelerate or speed up or slow down. Since there are no x forces, that's why the object continues to move in the horizontal direction with the same velocity that the plane does. Now, on the other hand, the object is experiencing y forces. It's experiencing the force of gravity, and the force of gravity is the only force in the y direction. Since there is an unbalanced force in the y direction, namely the force of gravity, unbalanced forces cause net forces. And since there's a net force, there's also an acceleration in the same direction. And that's why the object accelerates as it moves down. Watch the simulation again and notice what happens to the arrow in the vertical direction of the object that is being dropped. You'll notice that the arrow is getting longer. That's indicating that the velocity is increasing as it goes down in the y direction. The y velocity is increasing because it's accelerating due to the unbalanced force of gravity. So you can see that when we're dealing with a projectile, it's important to analyze it in two dimensions, x and y. We have to keep them separate. Let's look at that in another way. Let's suppose I was firing a cannonball from a cannon at the top of a cliff horizontally. Now, let's say I could magically turn off gravity for just a moment. If I could turn off gravity, once the cannonball was fired, it would continue to move the same amount of distance forever and ever and ever. Notice that the distance in between each dot per unit of time is exactly the same. And that's because the force of gravity, the force diagram, if gravity's not acting on it, is just a dot. There are no forces acting on the ball once it's shot. And since there's no forces acting on the ball, the law of inertia, or Newton's first law, comes into play. Being an object will want to keep doing what it's already doing. Now, we know in real life that there actually is gravity, and that's what's shown here in the x direction. Imagine that you didn't shoot the cannonball, but you just dropped it from a certain height. If you dropped it, it would start to accelerate downwards more and more and more, picking up velocity because of that force of gravity. Notice the distance in between each dot. Starts small, then gets a little bit bigger, and a little bit bigger, and so on and so forth as it goes down. The velocity is increasing in the y, but it's not increasing in the x. Now, when you draw these dots together, this dot with this dot, this dot with this dot, this dot with this dot, and so on, that's where you get the projectile path that we see right here. You'll see it's a little bit off, but you get the idea of what I'm trying to show. Okay? Where the x and the y meet is the actual pathway of your projectile. Now, how do we draw the motion map, the motion diagram for this projectile? Let's do that now. I'm going to erase these marks that I made so we can see clearly. What I want to do is I want to draw what does the motion map look like for a projectile. Since this object has no forces acting in the x direction, what that means is that its x velocity will always remain constant. So what I'm going to do is for each red dot, I'm going to draw the x component of the velocity. Notice that it never changes because the x velocity never speeds up or slows down. But that's only the x component. We also know that there's y component as well. I'm going to now draw the y components of velocity. Since it was shot horizontally, there is no vertical velocity initially. But then after a little bit of time, there's a little bit of y velocity, then a little bit more, and a little bit more, and it keeps increasing as it goes down until it hits the ground. This is how you would draw a motion map. Now I want you to analyze this drawing. Imagine a cannonball that was fired horizontally that took this path, and imagine a cannonball that was just dropped from the exact same height. Which one would hit the ground first? The one that's just dropped, or the one that's moving along a projectile path? The answer is the time would be the same for both. The time it takes for an object to just drop from a certain height compared to the time it takes for an object to fall from the same height going along a horizontal projectile path is exactly the same. And that's because it doesn't matter what's happening in the x direction. Falling and the time it takes to fall has completely to do with the y direction. And since the force of gravity is acting the same on both, they will both hit the ground at the exact same time. That'll be important when we go to the next video on doing the math problems. All right, let's go ahead and do a few checks with this idea before we end the video. Let's read this problem here. Supposing a snowmobile is equipped with a flare launcher that is capable of launching a flare vertically relative to the snowmobile. So imagine you're driving a snowmobile and you're driving at a constant velocity, and at some time you hit a button or trigger something that launches a flare from your snowmobile vertically in the air. If the snowmobile is in motion and launches the flare and maintains a constant horizontal velocity after the launch, so you don't speed up or slow down during any of this, where will the flare land, assuming, of course, we are neglecting air resistance? Will the flare land in front of the snowmobile, behind the snowmobile, or in the snowmobile? Maybe pause the video, think about it, and then hit play to reveal the answer. The answer is C. It would land in the snowmobile. Now let's talk about why that might be. To help you, let's look at an animation here. This isn't a snowmobile, but it's a truck. It's the same idea. It's going to keep playing over and over again so we can continue to look at the concept. Now, this truck is equipped with a vertical launcher that launches some object, we'll say a flare in this case, up vertically. As it's driving, it launches it in the air. Now, some students are tempted to say, well, wait, it's launching it at an angle. That's why it goes in a parabola. The truck is not launching it at an angle. It's already been moving in a horizontal direction. Think about it. Let's say the truck was moving at 50 miles per hour. So the truck's velocity is 50 miles per hour as it moves along this pathway. Now, when the object was in the truck, the object also was moving at 50 miles per hour. So the object had a horizontal velocity already going 50 miles per hour. What happened is when the object was launched in the air, now in addition to its horizontal velocity that it will maintain and already had, it now has y velocity. And as it goes up, it maintains the same horizontal velocity, but its y velocity starts to get smaller and smaller. Think about it this way. I don't have an image of this, but I want you to imagine a situation. I'm assuming most of you have either ridden on a plane, a bus, or a train, some sort of mass transportation that moves at a certain speed, a certain noticeable speed. Okay, so let's assume that we're standing on a bus, and you have a ball in your hand. As you're moving on the bus is moving. Of course, you wouldn't be standing on a bus because they yell at you for that. But assuming you were getting away with it, okay, you're standing on a bus, and let's say the bus is moving 50 miles per hour on the freeway. As you're standing on the bus with the ball in your hand, you throw the ball up. What do you notice happens? From your point of view, the ball just goes straight up in the air. But is the ball really just going straight up in the air? If you think about it, it's not. You and the bus and the ball are all moving at 50 miles per hour. You don't notice it, though, because you're part of the bus. You're on the bus. Now, from an observer from the outside, you and the bus are moving at 50 miles per hour, and so is the ball. And if an observer was on the outside of the bus and could look through the windows, when you toss the ball, they would see a parabola. They wouldn't see just straight up. Because the ball and the truck in this video both move at a constant velocity, they must be at the exact same point when it lands. We will do that sample problem in the next video.